Shoot.
So unsafe read, I assume that exists because you actually see some performance benefit from eliminating the bounds checks. Do you have benchmark data about that out of curiosity?
I don't have one I can show you right now, but I've seen the difference. It's a factor of 2 usually performance. Yeah, it's noticeable, absolutely. And especially if you try to change those operations many times. Let's say if you do a map and then a map, another map, and then something else, and then if each and every one of them would be doing those bounds checks for exactly the same array, that would be very, very wasteful. Okay, 06 mutable. This is what we went through. Let's go 7, computation. Okay. For this library, for Massiv, I implemented a separate package called scheduler, which is a work stealing scheduler. Who knows what a work stealing scheduler is? Okay. For those that don't, I will explain briefly. Essentially, what you do is you decide how many workers you're going to have, which is going to be just threads that get spun off in a computer. And then you create a queue of jobs, which are going to be just some actions that needs to be done, whatever that might be. And then those workers, let's say you have 4 workers, which on the quad-core computer without hyperthreading, and then you have 1,000,000 jobs. You don't want to, for 1,000,000 jobs, you don't want to spin 1,000,000 threads. Although technically it's possible with GHC, you still don't want to do it because it's extremely big overhead. What you want to do is you want to take those 4 workers, and each of one of them will be handling those jobs in the queue in first in, first out order. So you're going to take the job, compute it, store the result, and then the next job, and then the next job. It's non-deterministic which worker is going to do the job, because one job might be more expensive and then another is cheaper, so it can interleave, but they will be all performed. I do a little bit of trickery in order to make sure the order of the results is still the same as the order of the jobs that have been scheduled. So let me show you an example of how that works. By the way, don't be scared. There is not going to be any forking threads or M-bars or any of this concurrency stuff. This is all hidden, tested, works very well. We just able to use concurrency in a very simple manner. For this to work, we import control scheduler, and it lives in a scheduler package. And Massiv depends on it. Here is on my GitHub, if anybody needs it, to go and submit a patch or something, improve performance maybe. Okay, so we create, with scheduler, we give it the same computation strategy that you've seen before. So the options are seek, which is going to be running sequentially, just do the work in exactly in the same thread we are in. Par, which will spin as many capabilities as you have, which is on a quad-core computer with hyperthreading will be 8. Or you can use par n, which you just specify how many cores you want to use, how many threads to create. And similar with par on, I don't want to go into details what's the difference between par on and par n. Basically, on it will make spin up threads that are pinned to particular cores, so the thread is not going to move from one core to another. In reality, it doesn't make much difference, but sometimes it could. It could help with a caching problem, basically. Anyway, so what do we do? We created a scheduler, essentially. This way, we get a scheduler. This is just a data type scheduler that you can use in order to perform some cool things. But there's a bunch of examples on the repository. If you want to learn how to use it more, read up on it. It's fairly straightforward. There is not much magic there. But what we're going to do here is we're going to use the scheduler using the functional schedule work. Here's here's their types. Schedule work is just takes a scheduler that has some monad in it. It takes a job, and that's it. And it returns unit. It does some stuff to remember when this job's supposed to be run. And with scheduler, it creates a scheduler and gives it to your function. So this is what happens. We schedule something very stupid. You know, it's just add 10 to 1. Then there's a pure computation at 20 to 2, and so on and so forth. And then we run it. And we get the results of those computations. What happened here is scheduler library, it spun out 2 threads. It placed those jobs on a queue, so it was 5 jobs. And one by one, each thread performed the computation, and the scheduler then returned the list of results of those computations. That's all it is. Why is this even relevant? Well, you had a question, why do we want to have even I/O? That's the reason why. By the way, you see maybe something you're not familiar with, it's called monad unleaved I/O. I'm not going to dwell on the details why is it necessary. Just pretend that it's just I/O. Okay? There is a few monads, including I/O, that has an instance of this, like reader T, for instance, you can be used with it. But that's not terribly important right now. Remember the previous thing that we've done? What was that? 6 mutable. Oh, by the way, let me increase the font of this thing. Okay, so it's more visible. Let's look at this function. Oh, it doesn't fit full in the screen. There you go. And here we have the previous stuff that we wrote. Let's get it a little bit smaller. Okay, so we can compare. We start with the similar thing. We create a new immutable array, okay, which will be shared amongst the many threads. And we call this with scheduler. This is a different thing. We use the computation strategy that was this array was created with. By the way, we accept a source array, just as before, and then we return again a pure array, but this time it's in I/O. So what do? We see how many total elements this array has. We check how many workers the scheduler has, which is decided by the computation strategy. In the previous example I showed it was 2. Then we figure out how can we split up the work between those two workers. So we divide, let's say we have 101 element in the array, in the vector. We divide it by 2, and we get there's going to be 2 chunks of length 50, and then there's going to be a little bit of slack. There's going to be 1 chunk of element 1. This is what the slack started. It just records the indices, when do we need to start and stop. And we iterate those, but we iterate those separately. So we iterate from 0 to a slack start, and we jump the length of the chunk. So we're going to get 2 iterations of this loop, from 0 to 50, and from 50, and the next time is going to be 100. And each time we get an index. This is the same loop as before, but this time we schedule the work. Instead of loading those chunks, we tell the scheduler, go ahead and pick up this work. In the example I told you before, where array is 101 elements, we will create 3 jobs. 2 jobs here, we'll schedule 2 jobs, and this scheduler will create just 1. And what we do, we use this write computed function, which is just right here. And essentially, it's just exactly the same thing as we had before. It writes the element from the source array. And at the end, once this with scheduler function exits, once it's done running the jobs, the mutable array will be populated with all of the elements that we wanted, but it will do so in parallel. Does it make sense? Any questions? Okay. And this is the way we can automatically parallelize the work. Moreover, I'll tell you, this thing right here, despite being I/O, it is a safe operation. We don't return any mutable arrays. We don't do anything crazy. The threads that are gonna get spun up, they will be cleanly taken care of. They will be exited properly. So this is all safe. And in fact, what we can do, there is an operator called unsafe perform I/O, and in this case, it would be acceptable to use it. And in fact, that's what I do in Massiv library in order to do pure parallelized computation. And there are things, there are places where you can't do that. Let's say if the order of the result returned by the function would be different from the each time, depending on how many cores you have, for instance, such as, for example, a folding operator. If you want to fold, you need to also fold each chunk separately and then fold the results of those chunks separately, which means, depending on the cores, you'll have a different amount of chunks, and the results will be different. That's why you have to leave in I/O. I remember if I'm going to show that, but it's described in documentation in Massiv and with some examples as well. Let's go ahead and get rid of that. But whenever you see something like this, be very skeptical. Make sure there is nothing really bad going on there. And how about we visualize? Everybody likes visualizing, right? Nobody likes looking at code. Let's look at how this scheduler works in a visual way. We accept an array, a pure array, and we're going to create an array that contains colored pixels of which thread was doing the job. Okay? How it does it? It uses functions from control concurrent to get the thread number and capability. It's not terribly important. But what it does, it converts a thread to a color. And same way we freeze it. And what do I call it? I call it workers. Stack run workers. By the way, this pixel RGB comes from a library called Massiv IO. And it has all pixels, HSI, you can read images, write images. I'll talk about it later. And you see, I don't know which one is which thread, but they all different colors because I have 8 capabilities running on my computer. You see blue and so on, just like a Mauritian flag almost. Anyways, but here's a little bit of slack that was picked up by a pink thread because somebody had to do the work. And this is essentially how the array is getting loaded. Does it help conceptually? Yeah? No? Cool. Now, there is a question sometimes comes up. Sometimes you have an array that elements of this array are very different in complexity and how long it takes to compute. For example, Mandelbrot set, or ray tracing, or things like that. This nature. It can happen that in different areas there's going to be a bunch of cheap, very cheap computations, and in this sort of strategy, you will end up having one or a couple of threads doing most of the work, where other ones will be just sitting and doing nothing. What you can do, there is a special delayed array type called DI, delayed interleaved. All it does is you can convert any source array equal to interleaved. And what it's going to do, it's going to interleave each pixel, each element of the array. It helps with balanced computation. It's not cache-friendly, as cache-friendly as this, but in some cases, it's very helpful. I just give you for your information. It doesn't come up very often, but it can. Okay, and just so you know, this image was created also by Massiv IO. Let me go ahead and show you so you see that I'm not coming up with some. One sec. App main. Okay, here's the code. It calls this parent thread function with just a delayed array. Elements are not important, and it calls display image using a default viewer. True means you're just gonna block, and it computes and uses this function zoom with grid. That's what it did. It blew up an image 5 times. Also, you see using stride. It's not terribly important. You can look at the code later and try to figure out what it actually means. But it's done partially by Massiv IO, partially by Massiv. I don't know if I have a... Yeah, go ahead.
The fact that the pink thread did the last work, it's non-deterministic.
Absolutely.
So like, and so it's no longer deterministic because like we choose to show which worker did the work, but like if we didn't, we still keep the purity of like unsafe IO and everything.
Yeah, because
of that.
We don't care about the order exactly. We care about that all of them will do the job and finish the job. And by the way, if any of the workers at some point will throw an exception, like let's say division by 0, if you were doing pure computation that does throw an exception, it will clean up all the workers and rethrow the exception back to the main thread, so it'll look like exactly like a pure computation. And just to emphasize this, let's run it with a much smaller array. Probably should have increased the blow up. Yeah, let me do it this way. 15. You see, this array was much smaller. Some green and blue threads, they did more work, while the other workers, they didn't get a chance to do any work because they were still being scheduled. Well, I don't know, for some reason, if the jobs are very small, the same thread can just pick up so quickly and the others won't get a chance to do any work. And by the way, whenever you deal with small arrays, very often it's better to use sequential. That's why it is there, because spinning up threads still has some overhead. And very often for very small arrays like this, it will be more expensive to do parallelization. Again, only benchmarks can tell you the real truth. Okay. Are there any questions about this computation thing, about computation strategies? Because I'm not going to dwell about it much more.
Can you use a different computation? What was the name? Like, because you have different computations, right?
Mm-hmm.
And there, when you're calling with scheduler,
Mm-hmm.
you're taking the computation from array.
Mm-hmm.
Can you use another one?
Yeah, sure. You can put here par, right? And it will be fine. It's just it's gonna ignore the computation from this array. And some functions in Massiv they do that. It says so explicitly in the documentation, saying, you know, this function cannot be parallelized. For example, map m, or traverse, what we used to from traversable, cannot be parallelized because it's all sequential operations. And it will say explicitly so that whatever you supplied with your array, the computation strategy will be ignored. It will be done sequentially. Okay, good question. What's next? Next, let's talk about random. First, I'm going to use a function that does exactly what I just described. It does accept a computation strategy, but unfolding a sequential operator, it cannot be parallelized, so it says it hasn't. Asking here to kind of emphasize that. And it's just what you expect from unfold. it takes the size of the array, what you expect it to be, and then let's look at its type signature. Unfold R S, boom. There is quite a few of them. There is the right fold, there is left fold, there is one that you can get the argument of. Essentially what let me zoom it up a little bit. It takes the unfolding operator and sort of an accumulator that you can keep around. Where it is useful is, how many of you seen a splittable random number generator, which is a very popular package called random, for instance? Okay, for those that you don't know, how it works. It's a way to construct pure numbers. You ask a library to create a generator for you, which is just some data type gen. And then you have help functions that allow you to generate a number. But what it does, it not only accepts the generator, but it also returns to you a number, a random number, and a new generator. Okay, so you can chain those. You have to chain those operators. Not operators. You have to change those functions. If you want to create two random numbers, you need to call, give me a random number. It will give you a random number and a new generator, and that new generator you have to use in order to generate a second number. Because for the same generator, the number will always be the same. That's the principle. The cool trick is there is also splittable number generators, like a split mix or in random package. What you can do, you can take a generator and you can split it in two distinct generators, which will generate random numbers, different random numbers. They're not good for cryptography whatsoever, but for simulations and such, for property testing, they're perfect. Because they're pure, they don't depend on any state. They just have their own inner state that is pure. And this is what we do here. We accept a function, we accept generator, which is just some struct G. We accept a function that allows us to, using a generator, produce a random double number and a new generator. Okay? This is the unfold operator here, which we're going to use here. And the initial value is gen, which is this one right here. And using an unfold, we get a delayed load array with random numbers. Whew. That's how you can generate random numbers using Massiv. Well, actually, there is even a better. There is a specialized function already in Massiv that just does that. It's called random array, and moreover, it's automatically parallelizable. So using a splitting property, we can split a generator to how many cores we can have, and then run each core, each worker with its own generator and to generate random numbers. Let's see how it works. Okay, we created some pure generator using initial seed, just an arbitrary number. You can use I/O to get a random seed, a random generator using a system seed, and it gives us a two-dimensional array with the random numbers. And this thing system comes from package random. Similar thing here with the function I was telling you about, random array. It does exactly the same. And as you can see, using the same seed, it produces exactly the same array. Okay. Same thing. This is actually just using that. Let's run it. Same thing. Run it again. Same exact numbers, just because we're using the same seed. The interesting part is that the parallelized version is also deterministic, which is weird, but it is. Okay. There are random number generators, like a package called MWC random, that depend on state. They're not pure random number generators. They can be done in a C monad, just as before, and in IO, obviously. And they're not thread safe, so you cannot use the same generator across many threads. But here, how we would use it in a single thread in ST, we would use a function altfold r prim. We would give it a generator, and the generating function is still pure, so we can use that. And we generate random numbers using stateful. Yeah, right. Let's run it here. Using stateful random number generator, we can create a pure array just thanks to ST, but only single-threadedly. Same concept as we discussed before. It does all the crazy mutation nonsense, both in Massiv and in MWC package, and we hide it using the same principles as I described before. See this? There is this run ST, and fold r prim returns a prim monad. Same thing. Let's run this. This creates a seed from the system, so the numbers are different. I'm not going to dwell too much on it, but we can see how it happens. Create a seed. We generate an array. This function comes from Massiv. And we use the make random function that uses this st rank n types hidden state, and this way we can create a new array with random numbers and the next seed. If you ever need it, or if you ever need to deal with mutable things like that, just go ahead and look up it in the repository. It'll be always available. I'll keep it around as a good example. There is another PCG random number generator that works exactly, has very similar interface to MWC. I'm not going to talk about their properties. They just generate random numbers for all we care right now. There is also a random array IO function. I'm going to talk about it abstractly, and hopefully it will make sense. This was a recent addition to the scheduler package. But imagine this. You have a scheduler, and the threads, they are really oblivious to the state that they have. They share a mutable array, but functions that we map over the arrays, or whatever we do to the arrays, those functions don't know which thread they are running on, which worker. And it is important for random number generation, for the generator that is not thread safe, to be used only in this particular worker. So they cannot share it. And I came up with a way to initialize worker state, which is right here, which you can create a separate random number generator per worker, which is what it does here, PCG create. And then you can use that random number generator. It will be passed to this function uniform, which accepts a generator. But it will be done so in a thread-safe manner. It will be given exactly the same state, exactly the same random number generator that is supposed to work in this side. It's a lot of hand-waving stuff. But it actually, in reality, it's really cool. And this way we can parallelize stateful, non-thread safe random number generators. And I think it's really cool. And you see, this was, how do I say this? This uses exactly the same seed on both calls. So you see one thread working, there was two workers. one thread did the same numbers as the other. Okay. If we did create stem, I think that's it. PCG. I forget what the name. System create, I think. System create. Let's get rid of that. Just 1 second. You know what? Don't worry about it. I want to show this example. Import system random PCG as PCG. I think that should work now. No. Well, screw that. You get the idea. Okay. I also created a bunch of benchmarks. We're not going to go through them. I did it for separate reasons, but just to give you an idea. Random package, don't use it. It's extremely slow. If you use split mix, a new library recently developed by Alexey, it's much faster. It's also a split number generator with a very similar interface. This MWC and PCG, they're pretty good for all the non-crypto purposes. If you have any random numbers, you can use those examples how to get that done. Okay, let's move on. 09. Now, here, okay, we have 15 minutes. I think we can fit that in. Who knows what a stencil is? Nobody. Great. Think of it as a function that describes what you can do to elements of the array without knowing where you are in the array. You can index elements, but only relative to the center of a stencil. So for example, think of the cellular automata, the game of life. What the rules were. Look at the center, see if you're alive. Look at the center and see if you're alive, and then look at the neighbors. When you do this operation, you don't really care where you are in the area, where you are in the world. You only care about your neighbors. And this is what a stencil is. You can describe as a function these rules. And then using a separate function, you can apply this stencil to an array. Why this is important? Whenever you look at yourself and the neighbors for an array, you always need to check the bounds. Because if you are near the border of an array, of let's say a matrix, you can go out of bounds. And then you need to do something special. Like let's say use a default value or wrap around or something. You need to do that. But when you're in the middle of the array, you never need to do that. And that's the majority of where the time is spent. For this reason, there is another delayed representation called delayed windowed array. It uses a separate functions to compute elements inside of the array without doing bounds check, and a separate function on the borders while doing the bounds check. And using a stencil, we can make this operation safe. Let me show you. How cool is that? Here's our life rules. This is game of life. Think of it as a center of the more neighborhood. And this is the sum of the neighbors. How many total neighbors there are in a 3x3 square. There is, if I'm dead and I have, oh, let me zoom it up, sorry. And I have 3 neighbors, then I will become alive. If I'm alive and I have 2 neighbors, I'm still alive. I'm alive, there's 3 neighbors, I'm still alive. but otherwise I'm always dead. Also the rules. We create a stencil. A stencil accepts a size, which is 3 by 3, which is the neighborhood we care about. It's a more neighborhood. And we give it a center, which is in the middle, but there are use cases where you want it to be in a corner or whatever. And you get a function that you can use in order to index that, those elements of the array. It's not a simple function that just gives you an element. It gives you a value element. And it's done to prevent a function to depend on the indices himself. It's just to protect you from writing dangerous stencils. The stencil then is validated, and you can use it safely. Of course, as always, there is an unsafe counterpart that you can use. It's not going to give you any performance, but it gives you a little bit more extra functionality. If you can stick with the safe, stick with the safe. And this value, it's a function, it's an applicative. Therefore, you can do, you can fmap, and then you can apply this life rules function. So what it's going to do, it's going to apply this life rule to the center, which is at 0, 0, as far as the stencil is concerned. Then it's going to, oh, by the way, this value is also an instance of num, so we can just treat it as regular numbers. It's going to get the elements on all around the center, and it's going to sum them up. And in order to get a next iteration of the world in a game of life, what do? We call map stencil wrap live stencil. And it will give us this DW array, which is delayed window array, which we can compute if you want to. Compute and change it to S, right? And this is the whole implementation of game of life. Iterating this live step will give you consequent iterations of the world of in game of life. Now everybody's seen that, so I wanted to do something interesting, something a little bit more unusual, which I've implemented back in grad school, using, I believe I used array package from that came with base, and it was very, very ugly. It's a little bit more complex. I'll just go real quick through the rules. The instance loop, it looks at the Van Neumann neighborhood, which is top, bottom, right and center, or right and left, and this is the center. So it just looks in this neighborhood, and it's also symmetric. So it's gonna do so. It's gonna rotate it 4 times clockwise, basically. All it does, it expands the amount of states it can be in. And here's the actual rules. Let me go here. From the paper, we don't need to dwell too much on it. It essentially says, if your neighborhood is this and my current state is 0, then I'm going to be 0. And there is a total of 8 states. And I convert these rules into a very, very long case statement. And I give it an initial state, which is also from the paper. It's I don't think you can modify it in order to get a cool working example. This is the initial state usually. Then I will use a separate package that does printing to the terminal, and it converts each state from 0 to 7 to a separate color. They're usually pretty consistent amongst many implementations. But now let's look at what actually what it does. So this is the stencil. Just as before, did a 3 by 3 stencil with center at 1 on 1. And we get the function that allows us to index in relation. So we do just that. First, we get the center, which is this element right here. Then we get the top, which is -1, 0. Then we get the right, 0, 1. Get 1, 0, and get 0, -1, which is the left. I mean, this is pretty standard indexing. I hope you're familiar with that. And this allows us to create a stencil. Once you get used to it, it's pretty straightforward. And then you map the same stencil, except we have this stencil that just looks up the elements. It doesn't do anything to them. What we want in reality, we also want to transition to a new state. And the stencil is also a functor. In fact, it's a pro-functor. You see, there's two elements. This is the input element. This is the output element. And it is covariant in this argument. If you don't know what it means, don't worry about it. But I found it fascinating. Anyways, we take the lengthen stencil and we map a next state. What it's going to do at the next state, it's going to take the previous state, which is center, top, right, bottom, left, and it's going to rotate it. It's going to take this S, and then it's going to take those RBL, RBLT, BLT. So this way we follow the lengthens, the actual rules. And then we sum it. Okay. What do we also need? We need to initialize the array to something. The initial state you've seen, you're just going to take this state and it's going to use the function that we've seen already before, make load array. Cool. We're going to iterate over initial state, and we're going to write what this state contains. This is the initial state. And there is a little bit adjustment here, -33, just to make it work. The way to print the array, this is going to be our state of the lengthened loop. We're going to for loop over it. For every state, we're just going to print it in its own color. The rest, it's not particularly important. It just uses the helper functions from this module right here, system consolancy, to print stuff. The important part is this transition. This allows us to compute each new state and each new consequent array, and then print it consecutively. So let's go ahead and run it, see how it looks like. Okay, can you read this? It's pretty big, the array, that's why I minimized it to. Let's see. Hope it's gonna work. Boom. This is how it looks like. And it continues and going and going and going forever. And it's essentially a self-replicated machine. I don't find it particularly fascinating, except that it was invented in like 70-something. And it's something cool to implement, and it works perfectly for stencils. The other place where stencils are used is heavily in image processing, in a process called convolution. Quite a few other things they're useful for, and they're very, very efficient. And you can easily, the reason why they're really, really cool, they're easily parallelizable, because you describe in a pure fashion of how you deal with neighbors, and then that's it. We use the same process as you've seen before to load the array, and it's done purely and easily parallelizable. So, I think this is all I'm going to have for today. Do you guys have any questions? Do you want me to talk a little bit more on anything that I've covered so far?
I have one.
Shoot.
Could you please show the code again?
Yeah, of course. Mm-hmm.
And there's also a wrap thingy.
Wrap, yes.
How does it work? And like, is there alternatives to that?
Yes. There is a mirror, there is fill, if you want to fill a default value, there is I already forgot I implemented it like years ago. There's a few others. Any rule that I could find, I implemented basically. And you saw it was wrapping around. It was replicating on the other side of the screen. So that was wrap strategy. If I would, in this particular example, if I did what do you call it? Fill or something, any other one, then this example wouldn't work because it would run into a state that Langton's loop doesn't know, and it would just throw an error. It only works with a certain subset of possible states.
So that's more or less like a strategy, like you do map stencil, you did it like.
Yeah, it's just like a computation strategy essentially, but with a different domain. Mm-hmm. And besides that, it also checks the boundaries and stuff. And it's also used in safe indexing. Whenever you, let's say, you want to index an array, it does use the same functionality in order to check if it's within bounds. It's going to just use the fill to provide a default value. Mm-hmm. Yes?
And if that stencil is just a sliding window, would it be possible to vectorize these operations also?
You mean like SIMD instructions? Yeah. Technically, it's possible. In Haskell, it will be a lot trickier because they're not contiguously laid down in memory. If you look in top, bottom, left, right, you have to load them into memory, then load it in a special address in a CPU, and you won't get that much benefit. And you cannot do it automatically. You cannot parallelize it automatically, unless it's a sliding window on a vector, not on a multidimensional array. But it's a good question. And unfortunately, in Haskell, it's totally worthless. In something like C, you possibly could do that. But it's easy to parallelize it on multiple cores, though, which is what's done in Massiv. SIMD instructions would be very useful if you want to, let's say, we have a huge array, another huge array, and you want to multiply them, or matrix multiplication is very useful. Oh, and actually, I've totally skipped over one topic. I'm going to try to do it on Thursday. It has to do with slicing. You can take multidimensional arrays, and you can take chunks of it. Or let's say you want to take a second page, or you want to take a row, and it's going to do index manipulation for you rather than computing. And you can still do constant time indexing on it. And it's really easy to do. In a minute I have until I ring bell, I'll show it to you real quick. Yeah, not anymore. Okay.